Now I'm going to discuss z-scores and the normal distribution. The normal distribution describes what we would call a theoretical frequency distribution. What that means is that it's a theoretical mathematical concept that exists in abstraction that can apply to certain specific sets of data. But it is theoretical in that it exists more in an abstract sense. It's more of a concept that can be generically applied to different sorts of data. It is generated mathematically and is defined by an equation. It was derived based on an understanding of what we call probability theory. So this is the idea that for certain sorts of variables with certain sorts of samples and populations, we can generally expect a certain number of more likely outcomes, and we can quantify which outcomes are more likely versus which outcomes are less likely. The normal distribution is generally a pretty good description of some of the variables in psychology that we're interested in. Basically, the idea is when the normal distribution applies, we want the normal distribution to be approximated by our real life data. Again, the normal distribution is a theoretical frequency distribution, so data can be normally distributed even if it doesn't perfectly adhere to all of the properties and characteristics of the normal distribution. There will be some analyses that will require the data to be normally distributed in order for the analysis to be appropriate. You can evaluate whether or not your variable has achieved relative normalcy. If you violate that assumption, there would be certain statistical transformations you could do to make your data look a little bit more normal. A fair amount of psychology variables we can reasonably assume to be normally distributed, so this is an approach to analysis that does become relevant in some statistical analyses in psychological research. There's a somewhat interesting history to the normal distribution in that it was mathematically derived based on a series of systematic observations of various games of chance that rich people would play in Europe in the 18th century. Here's an example of what I mean by a game of chance. Let's say you're flipping a coin a series of times. Let's say you flip it 5 times. What if you wanted to chart the probability of any hypothetical outcome? We now have good solid probability theory that can help us map out the relative likelihood of getting 0 heads, 1 head, 2, 3, 4, or 5 heads. This would be an example of what we call a binomial probability scenario. Essentially, a binomial probability is any statistical probability-based scenario wherein you have a certain number of trials that have only 2 possible outcomes. You know one of those outcomes will occur on each trial, and you know the odds of each outcome on any given trial. This is just going to be one example of a certain probability scenario, but it's relevant to the normal distribution. Because if you were to map out the probability distribution that describes that scenario of coin flips, you would see that the probability distribution looks like this. Essentially, what you see here is a probability distribution in that what you see on the y-axis are probability outcomes quantified. So if you wanted to put this into percentage terms, you could just move the decimal place for any of those values over twice. So for example, the probability of getting 0 heads on 5 coin flips, you could see is right around 2.5%. Those outcomes in the middle of getting 2 heads, 3 heads, 4 heads, all of that is a little bit more likely, more in the 30% range. Those are the more middle of the road outcomes that are a little bit more expected. But you can see that despite the fact that it's a little bit more out of the ordinary to get 0 heads or 5 heads, those are still theoretically possible outcomes. A key observation is that this probability distribution is symmetrical. Now, this is just 5 hypothetical trials. If we were to chart the probability distribution for a series of 10 coin flips, your probability distribution would look like this. It's starting to take on more of a recognizable shape. As you can see, the shape is the same and it's still asymmetrical. It's just you have a little bit more of that sort of smooth curve on either side. Again, as you can see, those middle of the road outcomes in the middle 4 heads, 5 heads, 6 heads now in this case, those outcomes are all pretty decently likely. To get 0 heads on 10 coin flips, you can see is even more vanishingly unlikely than getting 0 heads on 5 coin flips. This essentially is a sort of a bare bones kind of a normal distribution. So the normal distribution was derived and mathematically defined by Abraham de Moivre, who was a statistician who developed the equation that can help you approximate the exact shape of the probability distribution for any number of trials or coins. That equation you see there to the right, you're never going to have to touch that with a 20-foot pole. This is just technically the equation that was derived by de Moivre to define the curve of the normal distribution. Again, there's a kind of interesting history where there were sort of chichi people in 18th century France who wanted to sort of game their little parlor card games, dice games, whatever. And so they actually wanted to hire out some statisticians who could help them do a little bit better at essentially kind of counting their cards, really just trying to figure out how they could best strategize their way to play the game to try and maximize their wins and minimize their losses. So a somewhat interesting history in terms of how the normal distribution came about. Again, as I mentioned, the normal distribution is a theoretical probability distribution. In more specific terms, what that means is that the normal distribution is not bound by any particular mean or standard deviation. For any theoretical mean and standard deviation combination, there's a unique normal distribution associated with that descriptive pairing. So the normal distribution can apply to any variable with any mean and standard deviation associated with it. For that reason, we say that there's not a single normal distribution, but rather a family of normal distributions. Again, what this means is that for any theoretically possible mean and standard deviation combination, there is a unique normal distribution for that pairing. Any normal distribution, though, is going to share certain key properties. Again, for data to be relatively normally distributed, it does not need to perfectly demonstrate these properties, but it does need to approximate the basic shape that we're about to see. Okay, so these visuals that we've seen before when I was talking about variance and standard deviation, all 4 of these curves would represent a normal distribution. The main thing you could visually inspect is that you're seeing the basic bell shape. The normal distribution is your classic bell curve. If you've ever heard that a certain exam was going to be curved, this is somewhat related to this idea of the bell curve of the normal distribution. For example, if your exam data was relatively normally distributed with a certain mean and standard deviation, the idea is I could reorient that very same curve, that very same distribution, around a higher mean, thus giving everyone a higher grade. So if you ever hear that something is going to be curved, it's partially because of this process. The basic properties that you can visually see on all of those distinct bell curves, the key features that they share, one is that they're all unimodal. That means there is one single score that represents the most frequently occurring outcome, right? That tippy top point of the bell is a single point. There is not more than one modal score. Again, in real life, a normally distributed variable might not perfectly adhere to this, but this is what the theoretically perfect normal distribution would look like, unimodal. Symmetry. This part is key, and you're going to want to revisit this point throughout all of the sorts of computations that you'll do using z-scores. The normal distribution is inherently symmetrical. In mathematical terms, this means that the mean and the median are the same value. That very middle value is going to be the mathematical mean with equal numerical weight above and below it, and that's going to correspond to the median as well. Again, this creates this property of perfect symmetry in your normally distributed data. Again, you can visually see its clear bell shape. In more specific terms, the maximum height is also going to live at that middle pole where the mean is. Additionally, the variable should be continuous such that for any value of y, there is a theoretically possible value for x. And additionally, you'll see that those tails are asymptotic. This term basically refers to the fact that those tails of the bell curve, theoretically out into infinity, would never cross the x-axis beneath 0. Again, these are the classic properties associated with the theoretically perfectly normal distribution. Try and think about how you could visually see all of those properties on a standard image of a bell curve. Now, additionally, based on the fact that the normal distribution is mathematically derived, we know that there's a precise relationship between the mean and standard deviation of the distribution and different areas underneath the curve. Basically, since we can mathematically define the normal distribution for any unique mean and standard deviation, we can use mean and standard deviation information to quantify different areas underneath the bell curve. This is going to be accomplished in a process of what we call putting our values in standard deviation units. This is going to quantify basically the distance of any individual score from the mean, as well as whether it's above or below the mean. So like I said, this has been mathematically defined. You don't need to do any calculus here. There are pre-existing tables and visuals that you can use to quantify various areas under the normal curve. So for normally distributed data, 34.13% of the scores lie in between the mean and a score 1 standard deviation above. This basically represents that taller area of the curve in between the mean and 1 standard deviation unit away. As you move further out into the extremes towards the tails of the normal distribution, right, the line of that curve is just closer to the x-axis, indicating a lower probability and fewer relative scores living in that area. So 13.59% of scores live in between 1 and 2 standard deviation units above the mean. As you move further towards the tails, that tail gets closer and closer to the x-axis, indicating fewer scores. So between 2 and 3 standard deviation units, you have 2.15. And once you're very, very, very extreme away from the mean, a very small amount of scores can be understood to be out that far away from the mean. So 0.13% of scores are going to exist above 3 standard deviation units. Additionally, as mentioned, the normal curve is symmetrical, so these exact same rules will apply and be mirrored underneath the mean. So 34.13% of scores will be in between the mean and a score 1 standard deviation unit below. This is what this set of areas underneath the curve maps onto. I will say right now, you do not have to memorize this visual nor the percentages. There will be a table that you can derive all of this information, but this is just a sort of a rough guideline for the percentage of scores that live under various standard deviation chunks underneath the normal distribution. Some other examples of variables that we understand to be relatively or perfectly normally distributed. You do see probability distributions end up looking perfectly normal. We're going to talk more about probability distributions in the next section when we talk about probability theory and computation. But if you're just mapping out the relative likelihood of certain hypothetical outcomes, like the likelihood of getting any certain number of dice rolls in a row, that probability distribution is going to be normally distributed. Other variables that we conceptualize as being normally distributed, IQ is a classic one. This is a controversial variable because classic intelligence questionnaires assess one facet of intelligence and discount others, but this is still a very commonly held construct that we generally think to be normally distributed. So if we measure people's intelligence according to classic IQ indices, we see that people's results are relatively normally distributed. We know the mean IQ score is generally 100, and you see a pretty clean normal distribution for IQ scores. Most of us are at or around average intelligence. You do have your outliers on both ends. For example, you've got your super geniuses up towards the right, like your Stephen Hawking's, and fun fact, Kesha, who is a Mensa member, she is brilliant. She's up there in that higher end, that extreme part of the IQ curve. If you were to chart out exam scores, a lot of time you're going to see data that looks somewhat like this. Typically not perfectly so, but typically you do see that center score, that mean score being somewhere in the middle, the average typically being somewhere around a B, and you see those more extreme scores of the Fs and the As just being relatively less likely. And even something like certain health variables like blood pressure. You can see that there's an average blood pressure that people tend to be at or around, and individuals with very, very high blood pressure or very, very low blood pressure are in relatively less frequency in the population, just because at those ends of the extreme, I'm pretty sure you die. So, diastolic blood pressure, relatively normally distributed. So, in figuring out why the normal distribution is useful to us as statisticians, the idea is that we know exact percentages corresponding to areas between each point in the distribution, any hypothetical score, and the mean. So, what we can actually do is we can determine any individual score's relative position in the distribution as long as we have our key information, our basic descriptive info that helps us orient our normal distribution. So, I'm going to show you all manner of practice problems showing you how you can play with z-scores and the normal distribution to answer all sorts of computational questions. So, to start, here's a hypothetical variable. Let's say I have individuals running a 5K race. I know that the average time to finish the race is 36 minutes with a standard deviation of 4. Let's say this 5K race is a WWE charity event, just because that example is fun for me. So let's say two of my individuals in my charity WWE 5K race. We got Goldberg, who is a giant hulking man who was pretty slow at 44 minutes, and somehow Ric Flair managed to release himself from his shroud of alcoholism. He finished that race in 31 minutes. You go, Ric Flair. So here's a question we can ask and assess using the normal distribution. How did Goldberg do relative to everyone else in the race? Goldberg performed in a 44-minute time to finish. That's 8 minutes longer than the mean of 36 minutes. You put that into a ratio with the standard deviation, and you put his value, his outcome, into standard deviation units. His outcome was 2 standard deviations above the mean because he was 8 minutes longer, so that's 2 standard deviations given the standard deviation was 4. What we can then do is we can use those percentages underneath the normal distribution to figure out what percentage of times were lower than Goldberg's. First off, you want to use what you know about the normal distribution. You know right off the bat that 50% of the scores in the distribution are below the mean, but you know Goldberg was not at the mean, he was in fact even higher than the mean. You know that he was 2 standard deviation units away from the mean, so you have to take into account that 34.13% between the mean and 1 standard deviation. And you need to take into account that 13.59% that lived in between 1 standard deviation and 2 standard deviation units. If the question is what percentage of times were lower than Goldberg's, it's a question of adding all those chunks together, because that gets you the percentage of scores that are below Goldberg's time. So Goldberg was at a 97.72 percentile. 97.72% of the scores were below his. He did garbage on that 5K. You can do the same basic process for literally any value in the distribution. The basic process is going to work like this. You're going to convert the raw scores into standard deviation units. That tells you where that score is located relative to the mean, which side of the mean it's on, i.e. higher than the mean or lower than the mean, and the distance from the mean. From there, you can determine percentage of scores above or below that spot. From there, you can answer a question about a percentile, meaning what percentage of scores are below a score. You can delete that percentile from 100 to get the percent of scores above that score. You can do all sorts of fun things once you figure out someone's standard deviation score. This standard deviation score transformation yields your classic z-score. So a z-score is this standard deviation conversion. A z-score is that value that tells you how many standard deviation units away from the mean any given score is. So z-score is going to be a transformation of our raw data just so that we can do different sorts of analyses with it. It's an example of a way to standardize all your values. Since the z-score is going to put all of your values into terms of relative distance from the mean based on that unique distribution, What z-score transformations accomplish is to put any hypothetical scale or spectrum of numerical values for a variable into a range from -4 to +4, because it's all about relative distance from the mean for that unique distribution. So you can take two variables that are on vastly different numerical scales. Standardizing them in this way puts them on the exact same quantitative scale. This is your basic equation for z-score. It's a very, very easy computation. To get a z-score for any individual raw score in the dataset, you take the deviation of that score, right? X minus X bar is the deviation, and you divide by the standard deviation. That gives you the z-score for any particular or individual score in the dataset. So now let's try doing some transformations to Ric Flair's score. Ric Flair had a X value, his outcome was 31. We're going to use the same descriptives for this variable, so a mean of 36 and a standard deviation of 4. And he has a z-score of -1.25. The two key pieces of information to take out of a z-score, one is going to be the sign and the other is going to be the absolute value. These two pieces of information tells you distinct things about any individual score. His z-score is negative because that deviation is negative, which means that his score was below the mean. Right off the bat, if you're drawing yourself a bell curve and you're plotting where Ric Flair's score was, it would necessarily be to the left of the mean because it's lower than the mean. Additionally, the absolute value of that z-score, meaning the value of the score when you disregard the sign, tells you about the distance of that score from the mean. So he had a z-score of 1.25, -1.25, absolute value of 1.25. He's closer to the mean than Goldberg was, because to evaluate relative distance from the mean, you just look at the absolute value, not the sign. Okay, so he was 1.25 standard deviation units below the mean. Again, the sign is important and tells you valuable information, and the absolute value tells you important, distinct information about an individual score. So again, z-scores can definitely be positive or negative. If you're computing the z-score for any value that's below the mean, you are going to end up with a negative z-score. If it's a score that's above the mean, that is a positive deviation and yields a positive z-score. Again, the position of a z-score is going to put that value relative to its own distribution. So this is why it's important to keep in mind the mean and standard deviation when you're computing these z-scores. The idea is we're putting any individual score in terms of its relative distance from the mean on the basis of the unique normal distribution that defines whatever variable we're currently contemplating. Additionally, an interesting property of this z-transformation process, the mean of a z-score transformation is always 0. Because think about what happens if you were to transform every single score in your dataset into a z-score. A z-score of 0 represents a score that's the mean, because any individual score that falls on the mean exactly has a 0 deviation from the mean. So what a z-transformation does is it reorients your data that has any hypothetically possible mean, and it reorients it around the value 0. Again, negative z-scores are below the mean and positive z-scores are above the mean. Z-scores of 0 represent the mean. So this process reorients your data to being on its own unique mean and standard deviation pairing, and it reorients it to the standard 0. Additionally, the standard deviation of the z-score distribution is always 1. That's because, again, z-scores represent a consistent scale variable to variable. So you could have scores that are clustered very, very close to the mean, or you could have scores that are quite spread out. The z-score transformation creates a standard deviation of 1. It basically can take any distribution that has any mean and standard deviation, and it transforms it into what we call the standard normal distribution. So again, you could be taking two different variables that are on extremely different quantitative scales, and you can make it so that those two variables have the same mean and standard deviation. And you can more easily compare between very distinct variables. Okay, so again, a standard normal distribution is a normal distribution that has a mean of 0 and a standard deviation of 1, typically accomplished by transforming every score in your dataset into a z and recharting the scores. Again, this is a process that we call standardization. Standardization. Okay, now let's move on to a distinct variable and do some more of these various sorts of practice problems. Like I mentioned, IQ is a pretty classically normally distributed variable with a mean of 100, standard deviation of 15. Let's take some of our same individuals. So Goldberg got a 110. Ric Flair, again, he's crushing it. Let's say he got an IQ value of 130. Hell yeah, join Mensa, Ric Flair. Then let's add a third individual. I know you all know John Cena, so don't act like I'm being crazy, okay? Let's say I got John Cena to take my IQ test. He got a 127. So I've got another variable, another mean and standard deviation, and I've got a new set of raw scores. So what's the z-score corresponding to Ric Flair's IQ score first off? You take the deviation over the standard deviation. Again, just computing a z-score is a very straightforward process. He has a z-score of positive 2. Like I mentioned, z-score transformations standardize very different variables. So whereas this IQ test is on a scale that's quite different from that 5K race, the fact that Rick's IQ z-score is the same as Goldberg's 5K result indicates that, relatively speaking, Goldberg is as slow as Ric Flair is smart. Again, this is the idea that despite the fact that IQ and 5K finishing time were on different quantitative scales, you are putting any individual score into a ratio that creates relative units of how far away that score is from the mean. Okay, so you can find the area under the curve for any raw score by doing this z-score transformation process. So now let's try it with Goldberg. You first, as usual, are going to convert that raw score into a z-score. Goldberg's z-score for IQ is positive 0.67. You're thinking to yourself, that clean graphic we saw earlier didn't have percentage in between a z of 0.67 and the mean. That's okay. Basically, the same question, the same type of question, right? If we're trying to figure out the percentage of scores below Goldberg, the basic process is to orient yourself on the normal distribution. You know Goldberg is above the mean, and we can chart out where exactly he is, right? He's somewhere in between a standard deviation of 0 and 1, and we specifically want to figure out what percentage of scores is below his. Well, we know that there's that 50% beneath the mean. The question is, what percentage of scores lives right there in that little chunk? Because if we knew that, then we could very easily figure out the percentage of scores beneath Goldberg. Like I said, that visual that I showed you of percentages underneath the 0 to 1 standard deviation, the 1 to 2, etc., you don't have that. You have a table that you will be able to consult to get these values, and you'll definitely have this table on the exam. What this table is going to give you is for any possible z-score, it's going to give you percentage of scores between that z-score and the mean. From there, you could use that information to calculate the percentage of scores from any z-score into the tail. Some tables will give you both. Some tables will give you both percentage between a z and the mean and percentage from z into the tail. But think about why that information would technically be redundant. You know an entire half of the normal distribution constitutes 50% of scores. So if what you have is just a table that gives you percentage of scores between z and the mean, if you wanted to use that to calculate percentage from that z into the tail, you would just subtract that percentage from 50%, and it would leave you with that z into the tail percentage. So you can sort of go back and forth, and you can use what you know about the normal distribution to do various calculations. Okay, so this, for example, would be a table that has area between mean and the z, and area beyond z. Zooming in a little bit closer, you can see that it has every hypothetical z-score, right? So for Goldberg's z of 0.67, you have area between mean and the z and area beyond z. These are in probability terms. As you can see, this doesn't say percentage. To use this exact table and turn it into percentages, you would just take those decimals that you see and move the decimal place over twice. This is giving you the same information that a percentage would. Now, one thing to note is that the sum of the value in any given row for area between mean and the z and area beyond z adds up to 50%, right? This 0.2486 plus 0.2514, those necessarily add up to 50, as does any one of these rows. So like I said, you don't technically need both of these columns for area between mean and the z and area beyond z, because you know they would inherently add up to 50%. Okay, so here's how you answer that question about Goldberg's percentile. From this chart, you know that 24.86% of scores would be in the area between the mean and a z of 0.67. You combine that with what you know about 50% of the scores being below the mean, and you very easily can calculate that 74.86% of scores are lower than Goldberg's. Goldberg is at around the 75th percentile. Now let's kick it up a notch and ask how we can compute percentage of scores that will be between individual z-scores. So what if we wanted to ask what percentage of scores are in between Goldberg's and John Cena's? You need to start by calculating a z for both. We already have Goldberg's. You quickly want to calculate John Cena's, right? He had a z of positive 1.8. What you're going to want to do from this point is, again, consult the table. From there, you would find that 46.41% of scores are between the mean and John Cena's score. We know from what we just did that 24.86% of the scores are in between the mean and Goldberg Z of 0.67. To find the percentage in between those two z-scores, you subtract 24.86 from 46.41. So 21.55% of scores are between them. In general, this is going to be because whenever you're comparing two z-scores on the same side of the mean, you will subtract the percentages to get the percent between them. If you were to map out where these scores are on a bell curve that you're just sketching, you would be able to see that the logic bears out that if you're trying to find that distance from Goldberg to John Cena, right, once you know John Cena's chunk, you know that getting rid of that chunk from the mean to Goldberg is going to yield you just the area from Goldberg to John Cena, right? It basically looks like this. You know Goldberg's here, you know John Cena's here. The idea is that if you know this distance from John Cena to the mean, and we know the distance from Goldberg to the mean, if we just want to get that area between Goldberg and John Cena, you take the John Cena from the mean, delete mean to Goldberg, and you're left just with this space here between them that you want. Okay, let's try another one. Let's say we add a fourth person who doesn't do quite as well on the IQ questionnaire. We add Rusev. He gets an IQ score of 91. Now, what if we wanted to ask what percentage of scores were in between Goldberg's and Rusev's? It's going to be similar, but slightly distinct towards the end. Once again, the basic process of conversion into z-scores needs to happen first. We already know Goldberg's. We need to calculate Rusev's. Rusev, as opposed to anyone else, you can see that his z-score is negative. That's because at 91, his score was below the mean of 100. So a z of negative 0.6. One thing to highlight here is that, again, the sign of the z-score orients you to above or below the mean. So Goldberg is above, but Rusev is below. Absolute value of the z-score is what tells you about distance from the mean. So relatively speaking, Goldberg is more distant from the mean, given that the absolute value of his z is 0.67, whereas Rusev was relatively closer to the mean with an absolute value of his z-score at 0.6. So what we're going to want to do is again use our table, and we're going to want to use that percentage from Goldberg to the mean, and now we need to know Rusev to the mean. Now you'll notice that in the table, there's no negative z values. That's okay because as I mentioned, you can get the relative distance from the mean, from the absolute value of the z-score. So since we're just trying to find distance from the mean in this case, you can look up in the table the percentage associated with a z of 0.6. Okay, so you don't need to have negative z-scores in the table in order to figure out the distance from Rusev to the mean. In order to find his relative distance from the mean, at that point you can disregard that negative sign. Once again, visualizing where these relative scores are, right, you can see that Goldberg is situated to the right of the mean and Rusev is situated to the left. Think about why it's a little bit distinct now that we're dealing with a score that's below the mean and above the mean in terms of what the last step is to calculate the scores between them. Okay, instead of subtracting one percentage from the other, in this case, we want to combine them. So the percentage of scores between a z of 91 and the mean, you add that to the percentage of scores in between the mean and a score of 110. That yields you a percentage of 47.43% of the scores are in between Rusev and Goldberg. So this is why in general, when you're trying to find the distance between scores on different sides of the mean, add those percentages together to get the total amount of distance between. Okay, now additionally, you can do this entire process in reverse. You can also find the raw score corresponding to any particular area underneath the curve. So this is basically just finding the scores associated with various percentiles. Whereas so far, we've seen examples of going from raw score to z-score to percentage, we're going to flip this process in reverse to generate some percentiles. So let's say I was to ask yourself, what score is the 80th percentile? This is essentially where you have to identify what raw score has 80% of scores beneath it. So you're starting with a percentage. You might be thinking, okay, I'm just going to go to the z table and I'm going to go to where it says 80% and find the z. Now it's not quite that simple. You need to stop and think again about the logic of the normal distribution. In the table, the percentages only go up to 49.99%. Basically, the table is only going to give areas for half of the normal curve. But think about why that's perfectly sufficient. Remember that both halves of the distribution are symmetrical. So you know that each half of the distribution holds 50% of the scores. What you need to do is think about what area of the curve are you trying to get to, and think about what percentage underneath 50 would enable you to get to the spot you're seeking. The 80th percentile is definitely above the mean because it's above the 50th percentile. Additionally, the 80th percentile has 30% of the scores in between it and the mean. Think about what I'm doing here. Basically, that 50% of scores that lives below the mean plus an additional 30% of scores gets you up to the 80th percentile. So what you want to do is you want to go into the table and you want to find the z-score that corresponds to a value that has an area of 30% of the scores between it and the mean, and that is a positive z-score. So again, think logically about why I'm doing 50%. It's because you can sort of take for granted the 50% of scores beneath the mean, but you know that your 80th percentile is going to be even higher than that. The question is how much higher? Okay, it's 30 percentage points higher than the mean. So 50% of the scores beneath the mean plus an additional 30 scores will get you all the way up to the 80th. So this is what you do. You go into the table and you find the z-score that has an area of 30% of the scores between it and the mean. You'll notice that the table doesn't have exactly 30% because it's operating under 2 decimal places. Just find whichever one is closer. If you choose the one that's above versus which one is closer, it's going to minimally impact your answer, but the general rule of thumb is just to choose whichever percentage is closest to the one you're seeking. So in this case, a z of 0.84 is a little bit closer to that 30% we're trying to find. So then from there, all we have to do is use our equation slightly in reverse. We now have a z-score, and we need to find a raw score. So really, we only need to solve for x. So we have our z-score formula. We're just using it a little bit differently. In this case, we need to solve for x. The easy way to do that is we're going to multiply both sides by 15 and then add 100. Think about the logic of why it is very necessary for that z value to be positive. What ends up happening mathematically is we're going to have a positive value to that left side of the equation, and then we're going to end up adding the mean to it. So if you have a z-score that is positive, when you go to solve for x, you will necessarily end up with a raw score that's higher than the mean. Okay, so in this case, you would just do a quick simplification and you would solve down to find that the 80th percentile for this particular variable corresponds to a raw score of 112.6. Some things to do here, for example, would be logically think to yourself, is this score higher than the mean? Does it seem to make sense that it would be the 80th percentile? Because the 80th percentile is definitely going to be higher than the mean, and it's going to be a fair distance away from the mean as well. Okay? Again, it's important at this point to think about the sign of the z-score before you solve. Given that I kept this as a positive z-score, the x that I solve for is inherently going to be above the mean. This is going to look slightly different if you're looking for a percentile that's lower than 50. Let's say I was asking you to produce the 45th percentile. This is going to be the raw score that has 45% of scores beneath it. So how do you do that? You're going to need to determine the z-score that corresponds to having an area between it and the tail of 45%. Now recall that not all z-tables have a column for percentage of scores between a z into the tail. But recall how I told you that you actually don't need that information because you can use the symmetry of the normal distribution to figure this out pretty easily. So if I wanted to find the z-score that corresponds to having an area from it into the tail of 45%, that would be the same thing as asking what score has 5% of scores between it and the mean. So in this case, you're going to try and find the z-score that corresponds to having 5% of the scores between it and the mean. Again, just pick whichever one is closest. So in this case, a z-score of 0.13 is a little bit closer, but this is critical. Since I'm trying to find a score that is definitely beneath the mean, make sure to change that z-score to a negative. Okay? This is the actual table from the Salkin text that you'll actually get on your exam, so make sure you know how to use it. Right? Since I knew I needed to find the z-score corresponding to 5% of scores between it and the mean, I now use that area between the mean and z-score column. I locate the percentage that I'm looking for, and then I pull out the corresponding z. Okay, so going in a little bit closer, again, this is what it looks like. This would be the area of the table that got me that answer. This here is a little garbage demonstration of how I do these little sketches to help me figure out how to do all these various z-score problems. Again, if that was hard to follow, that whole why did I choose 5% to get that 45th percentile, again, drawing a visual like this is going to help you out a ton. Key things to do when you're making a sketch like this: draw yourself a bell curve and orient yourself to what side of the mean you're trying to figure something out about, and then use that 50% on either side of the mean to help guide you. Okay, you can rely on the logic of the normal distribution to try and work out the information that you need. Basically, if you know how to compute z-scores, you know how to use this table, and you keep in mind just a few key characteristics that guide the logic of the normal distribution, You can do all of these kinds of problems I showed you. You can figure out distance underneath or above a score. You can figure out distance between individual scores, and you can figure out percentiles either above or below the mean. Okay, so again, in this case, we need to solve for x as the last step. Again, we're using the z equation just slightly in reverse, and again, since that 45th percentile is below the mean, make sure to turn that z-score negative before you solve for x. Again, think about what happens mathematically when that z is a negative before I start solving. I'm going to multiply both sides by 15, and I'm going to be left with a negative value on the left that I'll add 100 to. Adding 100 to a negative value is necessarily going to yield a raw score below 100. So make sure, if you're looking for a percentile below the mean, that you get that z-score changed to a negative before you solve. So in this case, your 45th percentile is a raw score of 98.05. Again, think about the logic here. Does that answer make sense? That raw score is below 100, but not very far away, which the 45th percentile would be. The 45th percentile is going to be quite close to the 50th percentile, which is the mean. So that answer logically shakes out. So again, 98.05 is my 45th percentile. I encourage you to do the practice problems that I've made available because I know it can be tricky to get your head around the various z-score problems, but I promise you, if you just think about the logic of the z-scores, you should be able to get it no problem. Now, if you wanted to do your discussion post this week on z-scores, the idea would be to see how z-scores actually might be used in real published data. So this does happen some of the time. Certain variables, researchers have statistical justifications for doing a z transformation because essentially what this accomplishes is, again, standardization, whereby, let's say you have a variable like BMI, which you sort of necessarily expect to be different in different age groups. Researchers who study BMI and how it's associated with other health characteristics and psychological characteristics want to make sure that we don't just look at someone's weight, we look at their weight compared to their age group, because different age groups will have different BMIs and the range might be a little bit different. So researchers who study BMI will often standardize that variable such that all of the participants in the data set are being compared to one another. So this particular article that I've linked here is an example of a paper where researchers did this standardization process. They did make sure to justify why they did that and explain that BMI is often z-transformed. And they explained a little bit about how it applied to their analyses. So if you wanted to use z-scores for your discussion post, basically just find any other article on PsycInfo that includes z-scores or z-transformations. A fair amount of health variables, so definitely BMI, but other health variables as well, are going to do this z-transformation, so that's sort of a lead if you're interested in trying to find a z-score oriented article. So if you find any article that includes z-transformed scores, just discuss what the variables are that were subjected to this transformation. That'll do it for this lecture on z-scores. I hope you guys are doing well, and I'll talk to you soon.